A Schmitt trigger is a comparator circuit with hysteresis that provides clean, noise-immune switching between two voltage levels. When a signal hovers near the threshold voltage and contains even a small amount of noise, a basic comparator can misinterpret it. The output toggles multiple times, falsely indicating multiple transitions. In reality, the noise isn't a valid trigger, but the comparator treats it like one. To resolve this issue, Schmitt trigger is needed. A Schmitt trigger adds hysteresis, meaning the output is influenced by both the current and previous states. It has two thresholds, but only one is active at a time. When the input crosses one threshold, the active threshold changes to the other. This prevents output toggling from small noise near the threshold, ensuring a single, clean transition. There are two types of Schmitt trigger, inverting and non-inverting. In inverting Schmitt trigger, the input is applied to the inverting terminal of the op-amp, or comparator. The output switches in the opposite direction of the input. A portion of output voltage is connected back to the non-inverting terminal of the op-amp. This makes this op-amp configured in positive feedback. In non-inverting Schmitt trigger, the input is applied at the non-inverting terminal of the op-amp, or comparator. The output switches in the same direction of the input. In a positive feedback circuit, output will always saturate near power supplies, either VCC or VEE, so it can have only two states. To understand, let's break the loop here. Now let's apply a small positive voltage at the non-inverting input, while the inverting input is held at 0 volt. The output grows in positive direction. Some portion of this growing output comes back at the non-inverting terminal and raises the non-inverting terminal's voltage again. This leads to more increase in output voltage. This continues till output grows and saturates near the supply. When the output is saturated near VCC, the non-inverting terminal voltage is set by the resistor divider formed by RG and RF, establishing one threshold. To toggle the output, the inverting terminal must exceed this level. When the output toggles and saturates to VEE, the same divider sets a different voltage at the non-inverting terminal, creating the second threshold. To illustrate the concept, we'll use an inverting Schmitt trigger as an example. The output is originally saturated at VO max. The threshold is VUT, which is called upper threshold. When the input crosses the upper threshold, the output toggles from high to low and saturates at VO min. With that, the threshold changes as well. This new threshold is called lower threshold, VLT. If the input later returns above the original threshold, the output remains unchanged. If the input goes below the lower threshold, the output reverts back to VO max, which is its original voltage. Non-inverting Schmitt trigger will have opposite input to output relationship. In the right, we have complete hysteresis curve. The grayed portion is called hysteresis window. It is mathematically represented by difference between upper and lower threshold voltage. The resistor ratio and the output voltage swing, delta VO, decides the hysteresis window. We can change the threshold voltages according to our needs and also adjust the hysteresis window. This makes a symmetrical Schmitt trigger into a non-symmetrical Schmitt trigger as shown. All we need a comparator or op-amp without hysteresis and configure it in positive feedback. Let's go through an example where we design a comparator with hysteresis. The desired comparator threshold voltage is +2 volt. The desired hysteresis is 200 millivolts. This will make this comparator immune to noise amplitude of less than 200 millivolts. To start, we can tie the Vref to +5 volt as it is readily available voltage in form of VCC. Delta VO is 9 volt. Following the relations shown, we can calculate RH and RG. In the right side, we see the comparison between a basic comparator and a comparator with hysteresis. The top window shows the rising input with some noise, the threshold voltage of basic comparator and threshold voltage of comparator with hysteresis. The basic comparator has a fixed VT. The input crosses it multiple times, resulting in multiple output transitions. The problem is solved using the example shown, where the hysteretic comparator changes the threshold as soon as the input crosses the threshold once. This results in only single output transition, which is desired. The 74HC14 is a hex Schmitt trigger inverter IC, meaning it contains 6 independent inverting Schmitt trigger. It operates on a 2 volt to 6 volt supply. They are a good alternatives of NOT gates in noisy environments. In the left, the IC package diagram is shown. In the right, we see the internal threshold voltages varying with supply voltage VCC. VEE is fixed to 0 volts. The gap between the two threshold voltage is typical hysteresis window. The gray region signifies the possible variation in VUT due to manufacturing process, temperature, and supply voltage. Similar variation happens in VLT. This is an optimized complementary MOS implementation of inverting Schmitt trigger by Filanovsky. It is suitable for integrated circuit implementation because of low transistor count. Using a Schmitt trigger, we can create a relaxation oscillator which can produce square wave. We've seen how op-amps and comparators can form robust Schmitt triggers using hysteresis. Thanks for watching. And as always, like, share, and subscribe for more analog circuit content.